this video, I'd like to solve a problem of something being thrown off a cliff. So our problem is that we have a cliff. We're told the height of the cliff. The height of the cliff is, let's say it's 200 meters, very high. And an object is thrown horizontally at a speed, let's say it's given initial impact of 10 meters per second. Now we expect that this object, when it's thrown horizontally, to eventually hit the ground. And the question is, where does it hit the ground? I'd like to know exact position where it hits the ground. And this is an example of basically using vector equations. So we have a mass, an object that's thrown vertically. Maybe I throw a baseball and I have a very strong pitching hand apparently. But that pitching hand throws the ball, and this ball travels at 10 meters per second. And it hits eventually horizontally. And so what equation should I be using? Well, for constant acceleration, the two equations that you should really be familiar with is, when you're looking at constant acceleration, A is a constant. Then the two vector equations that you need for constant acceleration are V final is equal to V initial plus acceleration times time. And the second equation that we need to know when we're looking at constant acceleration is that the displacement, the final position, displacement final, is the initial displacement plus the initial velocity times time plus 1/2 a t squared. Notice the acceleration and v are vectors. T is just a scalar value. So these are the two equations that I'll be using to solve this problem. And mostly I'll be using the second equation, if anything. We know that all objects, right? So we'll start writing the equation. So let's write out. Now before we do, we have to create a coordinate system, and you should always do this. Draw a rough diagram of everything. So here it is. Here's a cliff. The height is 200 meters. The velocity v is 10 meters per second, and it's going roughly horizontal. So I'm going to create a coordinate system where the origin is right here. And this will be the first time I'm selecting the direction I is going to the right this time. So instead of, usually I would use I to mean east and J to be north, but in this case I'm going to select I to mean to the right, and J vector is going to be up. So J vector is up. So what are we given? We're given the initial velocity, the magnitude of the velocity is 10 meters per second. We're also told the height of the object. The height of the cliff, the height of the cliff is 200 meters. We're also told something else, and that is that we're at the surface of the Earth. Hopefully this is at the surface of the Earth. And if it is, we know that the gravitational acceleration g is given by a quantity 9.8 meters per second squared. In these calculations, I'm not going to worry about the units. I won't worry about the precision of our calculation. I'll assume that everything is correct up to 2 significant digits. So we should be more careful in this, but I'm trying to teach a major concept to make sure you know how to apply vector equations. So I'm not really worried about the precision of your answer. So don't worry about that. Spend time thinking about how I can apply these vector equations to constant acceleration. So let's write out what we know. Well, we're going to be using distance df di plus vit, this second equation. So this is, what's the initial position of the object? Well, the initial position of the object is, hopefully you can read this off, the object is right here at time t equals 0. It's initially at the top of the cliff, right before it's being kicked off. At that point, right, we know that you just have to go up 200 meters up to get to that point. Now, I'm not going to use 200. I'm going to say that since we have a symbol h, you should try to use variables as much as possible and say this is hj. That's the initial position of the object. It is 200 meters up. Notice I'm using j to mean up. Before I was using j to be north, but now I'm using j to be up, and I to, instead of using east, I'm now saying it's right. So when somebody reads this off, it should be 200 meters up. What's velocity? Well, the initial velocity is going this way, this direction. So I can say that the velocity vector initial is 200 meters going to the right. So I can write that quickly by just writing v. Notice I'm not using numbers, I'm using symbols. You have to get used to this in physics. So vi. And what else? What is the acceleration? The acceleration, right? Acceleration A is, it's going down. The acceleration is down. And how do I say down? It's minus g, and the down is negative of up. So minus g. So we have three equations. Sorry, three values for the vectors. And guess what? We have di, vi, and acceleration. So if we know this, we just plug it in. So we don't know exactly what time it lands. We don't know where it lands, but let's plug into the first equation. And we can try the second equation, but as I know the answer, and you'll start getting used to this, but I actually will be using the second equation. So let's plug into the second equation and look at it. So this is d initial plus v initial times time plus 1/2 a t squared. So these are vector equations. So di is h, j. Hopefully you're getting used to these component forms. So here is vit, which is just vi, times time, plus 1/2. Acceleration happens to be minus g, j, times t squared. So let's expand. hj, v times t, a vector scaled by t is just vt, I. And sorry, that's supposed to be a plus sign. And then there's a minus 1/2 g t squared j. And then move the j's together because traveling in the north or the up-down direction is unrelated to traveling in the east and west direction or right to left. So this is now vt I plus, and I'll put the j in front so you know that the order doesn't matter. You know these things, they're just placeholders for things. So this is h minus 1/2 g t squared j. Whatever this is, we don't know what t is, but this tells me that the position of the object for any time t. So if I knew what t is, I can tell you the position of this object anytime. So this is our equation that we want to deal with. So at any time, if t is equal to 1, I just plug in value of v. v is 10, t is 1, h is 200, 1/2, 9.8, 1 squared, and I get myself a position in space. So it tells me exactly at different times, for example, t equals 0. When t is equal to 0, then the position is going to be 0i, or 0 to the right, and this is 0, so hj. Oops, I wrote down j twice, so that's a mistake. So let me take that off. Actually, let's put the j on the end, okay, so it might look more nicer. But the order doesn't matter. So if t is equal to 0, we know that you're at the initial position of 200 meters up, hj. So when does it land? So the question is, what time does it land? So let me erase this portion so I can look at it more carefully. So I don't need all this because I've written everything down. I have the equation. So when does it land? Our question is, at what time does it land? Right over here. But if you think about it, right, I don't know what time is, but I know that when it hits the land, right, its position, right, must be in the vertical position, the up and down position must be 0. So when this term, right, is 0, that's when it lands, because it just ejects out and comes out this way. So at some time it's going to hit the x-axis, and this x-axis is when the vertical position, the height, is 0. So in this case, this whole height, right, of the position of the object must be 0. So that occurs when h minus 1/2 g t squared is equal to 0. So that's the time that it'll hit the ground. So we can solve for this. So I'll move the h to the other side. H multiplied by 2 divided by g and get t squared. We solve for t by taking the square root, so t is equal to the square root of 2h over g. So this is the time. Now there's a plus or minus, and the minus corresponds to something that happened before the initial instant. So that's not important to us. It has to be something that's forward in time. So this is actually a plus, not a minus, even though the answer, right, you're expecting two answers. So again, I moved the 1/2 gt squared to the other side, and then I multiplied by 2 and then divided by g. So I skipped a couple of steps, but please do write them in. If I went too fast, then you should write them in more carefully. So this is the time where the object hits the ground. But now I know exactly what happens. When it hits the ground, this value becomes 0. But what is that time? So let's put th to be the time it hits the ground. Time at ground hit. At ground hit. Hits the ground. So time at ground hit. So what is the vertical position at that time? Well, it's vt. So I know that this is the x position at any time t. I'm kind of scribbling right there. And my marker is dying too, so get the marker. So this is what I'm looking for. This is v times the time when it hits the ground. So if you want to call this x hit, so we can write this x hit position where object hits ground. Wow, that's a lot of English to write. Yeah, which is just VTH. But I know what VTH is. It's V. TH happens to be the square root of 2h over g. And I can plug in numbers at the last step. So if you want to find xh realistically, so in your calculator, you just plug in the last step. So this would be the velocity, which happens to be in units of standard units 10. And then we're looking at the square root. So 2 times height of 200, standard SI units, all divisible by 9.8 meters per second squared to the 1/2. So this is what we calculate, and that would be the x position. So in this problem, I'm trying to get you used to using our notations of I and j. Once you do, you'll actually see a lot of these problems are pretty straightforward. They're not complicated. They're not fraught with looking at the components in different dimension and stuff. We're just using state symbolic manipulation to get an answer. So the whole thing is that the object is fully described by this equation, and when it hits the ground, I happen to know that it hits the ground when it hits the x-axis, so the y component must be 0. And if the y component is 0, it's this component. I solve for th. Once I know th, I can plug back into here to get the x position, and that's what I did over here. Finally get the answer.